Hey everybody, Dr. A here. In this short video, we are going to begin our first discussion on dead loads of structures or materials in general, okay? So let's go ahead and get started. What is a dead load? Well, recall that dead loads are permanent loads acting on or attached to a structure. Okay, so that's the basic definition of a dead load. It's always going to be there. It's always attached to or acting on a structure. It's going to be there for the entire life of the structure. Okay, now dead loads often act in a downwards vertical direction on a structure. Okay, we call the downwards vertical direction the gravity direction. Okay, so when we are thinking of dead loads, most often they're acting in a downwards vertical direction. Every now and then you may encounter a dead load that's acting in some other non-vertical direction. So let's draw a little figure of this. Let's say that we have a frame type of structure here, okay? And I'm just drawing this, maybe this two-story frame here, okay? So when we think of the dead load of this floor right here, okay, the dead load of this floor may be treated as a uniform distributed load. So we can call this like Q sub D, Q dead, okay? And so when we say it's acting in a downward vertical direction, we think of it acting just like I drew it here, a uniformly distributed load acting downwards on the floor, okay? Now, usually dead loads, they may be expressed in different types of magnitudes, okay? So we often will see dead loads expressed first in terms of a force per unit area, okay? So dead loads are often expressed with units of force per area, okay? So I'm going to draw a little 3D sketch of this. Let's say we're looking at this floor load right here, but I'm going to look at it in 3D, so kind of like the dimension coming out of the screen at you, all right? So if I draw this that floor dead load in 3 dimensions, okay, let's say that this is my 3-dimensional floor. And so what we would think of is this dead load acting over the surface of the floor, kind of like I'm drawing here. Now, please forgive me, I'm not the most prolific artist in the world. But think of this as like a vector field all acting downwards, okay? You have this this set of vectors acting in the downward direction, okay? And so you can think of this as a surface load, okay? This is a surface load acting over the entire square footage of this area. So let's say that maybe, you know, this dimension is B, and then maybe this dimension right here is L. So if I were to go back and look at my original 2D dimension, where would the dimension B be located? Well, that would, you know, be maybe right here. This dimension line right here is B. So so again, this is not my best artwork, but this is a surface load. So this, you can think of these vectors this whole surface, this area of B times L has a load spread out over it. And so again, we'll often call this, Q. We use the letter Q, and if it's a dead load, we'll put a subscript D there, and we say it's got units of force divided by area. Okay, now if we want to kind of collapse this into a single resultant point load, right, acting right through the centroid of that area, let's call that P sub D for P dead. How can we do that? Well, we can say P dead equals that surface dead load Q dead times the area over which it's acting. Well, that area is the surface area that Q dead is acting over. So we can call that Q dead times B times L. And of course, we would see that P dead comes out with units of just force. Okay, so so then my follow-up question for you to think about is, how do we determine minimum design dead loads, or just dead loads in general? Well, we determine dead loads from material properties. Like what? What are some material properties? Like density, oh man, technology, right? Like density, unit weight, and specific gravity. Okay, so that's one way to determine dead loads, through a materials properties like density, unit weight, specific gravity. So our reference, a common reference that we can use to help us find some material properties, is our ASCE 716 standard. So ASCE 716 table C 3.1-2 gives minimum densities, or another way you can think of that is unit weights for common construction materials. Okay, now these densities or unit weights typically have units of like pounds per cubic foot or kilonewtons per cubic meter. Okay, but it's a big table that has a lot of different common construction materials, and their densities are unit weight. Okay, now another way we can determine minimum dead loads is by ASCE 716 table 3.1-1A, okay, and B for that matter, A and B. So I'll make a note of this. ASCE 716 table C 3.1-1A and B gives minimum design dead loads in force per area for common construction materials. Now you may be wondering, what's the difference between these two tables, right? Or these two types of tables, okay? So one of them the first one we talked about gives minimum densities or unit weights. So remember from a materials course that a density or a unit weight specifically has units of force per volume, right? So that's like pounds per cubic foot. kilonewtons per cubic meter, okay? Whereas the second table I made reference to, or it's actually two parts of the same table, C 3.1-1A and B, give minimum design dead loads in terms of force per area for common construction materials, okay? So this is like going to be given in pounds per square foot or pounds or kilonewtons per square meter. So a thickness dimension has already been factored out of this table C 3.1-1A and B, okay? Now, you can use either table depending on like what you're dealing with. Depending on the type of construction material you are working with, you may end up using, you know, one of these types of materials like a density or unit weight term, or you may end up using the minimum design dead load and force per area, okay? So it just depends on your specific situation. So this concludes this video on just kind of the background of dead load specifically. So if you like this video, please hit like and subscribe.